Hello, and thanks for watching this video. I'm Hamad Hamid from MIT. In this video, I'll be telling you about my research on self-reconfigurable microimplants for cross-tissue wireless and batteryless connectivity. This talk is about how we can design tiny intelligent microchips like the one in my hand here and implant them inside the human body for medical sensing applications. In this project, we set out to build microchips like this one, which has no batteries, and put it deep inside the human body, and we wanted to communicate with them from outside the body. Our approach is to use wireless power. A device outside the body shines a wireless signal which goes through the body. When the signal reaches the sensor will harvest energy from it, power up, and communicate with the device outside. This will enable many applications in digital medicine, such as long-term drug delivery, nanosensing, and neurostimulation. But before I tell you how we built our system, Micromedic, let me tell you why bringing batteryless connectivity deep inside the human body and across tissues is very difficult. Let us say I designed the microimplant so well that it can power up and operate inside the stomach. Indeed, a few years ago, we demonstrated the potential to power up microimplants deep inside the body. But if I take the same microimplant and put it somewhere else inside the human body, for example in the large intestine, it does not power up, even if it's the same depth inside the body. And the reason is that the surrounding tissue will impact the microimplant properties and prevent it from harvesting enough energy to power up. The problem is that antenna resonance is impacted by surrounding tissues. For example, let's put the implant in a muscle-based tissue like the stomach. Plotting the harvested energy versus frequency, you can see that this antenna was optimized for muscle with a peak around the 900 MHz ISM band. However, if we put the same implant in the fat tissue, the peak shifts to around 1100 MHz, which is why it can't power up inside the ISM band. The reason this happens is that to maximize efficiency, in-body antennas are typically designed to be resonant. However, such resonance changes when we change the surrounding medium of the antenna. Specifically, in-body antennas are designed as rigid loop antennas, resonating directly with the harvesting chip. If you plot the energy harvesting voltage versus frequency, we get a single peak. Resonance is the natural frequency at which something vibrates. For example, if I plug this glass cup, I hear a specific tone that corresponds to its resonance, or natural frequency. And this resonance is fixed. To overcome this, our idea is to introduce a coupled structure in order to control resonance. Having two antennas close to each other typically results in an undesirable phenomena called coupling. This changes the harvesting properties, as you can see in the plot here. But in our case, we want this coupling so that we can shift the resonance frequency and build a programmable antenna. And we do this by adding a tuning capacitor bank that controls the coupling, allowing us to shift the resonance. While I've explained this at a high level, in the paper we describe how Micromedic builds on this idea to enable full programmability of its antenna, harvesting circuits, and communication logic. In doing so, it enables wireless and batteryless connectivity and availability across tissues. We implemented Micromedic's design as a fully integrated chip, fabricated using TSMC 65 nanometer low-power process. The chip is around 1 millimeter squared. We also designed and fabricated our coupled antenna design as printed microstrip on a flexible PCB substrate. Here's one of our sensors in my hand. As you can see, I can roll it into a pill form or potentially laminate it on an organ. And here's a magnified micrograph of the die. The chip has different blocks, including those for programmable antenna tuning, tunable matching circuits, the logic, energy harvesting, power management unit, and transmitter and the receiver. The chip also incorporates a MAC protocol, and we implemented a radar to power up and communicate with it from outside the body. We've tested our device in different environments, including both in vitro and ex vivo setups with tissues. In a nutshell, Micromedic is a wireless, batteryless, and self-reconfigurable microimplant. It's the first system that enables cross-tissue wireless and batteryless connectivity. It's also the first batteryless microimplanted system capable of self-reconfiguration for energy harvesting and backscatter communication inside tissues. We've designed, fabricated, and evaluated our microimplant in different tissues, including both in vitro and ex vivo environments. and our results demonstrate that it consumes 350 nanowatts, supports up to 6 megabit per second, and can operate across tissues. I want to wrap up this video by saying that this research is very exciting for me because on one hand, it bridges ideas from various disciplines, and on the other hand, it paves way for a new generation of medical devices that can be used for disease diagnosis and treatment. Thank you very much for listening.